Hi there. Welcome to the design of pre-stressed concrete with the post-tensioned concrete emphasis. The year right now is 2022, but these videos likely will not be seen until the spring quarter of 2023 at UCLA and Cal Poly. We are in discussions with having these videos used kind of globally through a company. So we'll see what happens there. I am likely right now, if this is the spring 2023, or 24 or 25, I'm hoping to use these videos more than 1 year. But I'm likely at the ACI convention right now. I am on 318T currently, hoping to get on ACI 320. And ACI requires that you show up in person if you want to keep your position on committees. So that for COVID, they made it kind of easier. We can get in there on video, on Zoom, but they're back to in person for now. So that's likely where I am right now as you're watching this. I want to give you the history of this class, design of pre-stressed concrete. Pre-stressed concrete has never been more popular in construction and in the practicing world than it is right now. It has just gained popularity tremendously, and really over the last 10 to 15 years. It's always been popular since the 50s and 60s in some areas, but it's growing geographically in popularity, and firms that were afraid of it are now embracing it. There's all kinds of software to design it, and everybody's jumping in the pool. However, with all that happening, you would think that the academic world would be also jumping on board and expanding their teaching and making sure they have qualified people teaching these classes. The exact opposite has happened. Schools across the country have stopped teaching pre-stressed concrete design. I think according to PTI, there were only about 22 schools that were currently offering design of pre-stressed concrete, and most of those were only teaching single-span precast pre-stressed concrete members. So this class is really a post-tensioned concrete class, which is an entirely, almost entirely different thing. We're going to learn both in this class, but over the course of the course, you will see the differences. But this class, so I started reteaching again. I taught in the 90s at Cal Poly Pomona, but I came back, was asked in 2011 to teach design of pre-stressed concrete at UCLA. Ironically, my father had taught that same course in the 1980s and 90s, and I had been asked to teach it a few times over the years since he stopped, and I'd always declined. But in 2011, we were in a pretty serious recession, so I needed something to do, and I accepted this time. They didn't tell me when they hired me in 2011 that they were not going to offer the class in 2012 or any year after that. That was it. That was to be the last time. So I don't know. There's some I don't know. The fact that they were using the son of the person that had taught it for 15 years or so was poignant somehow, I guess. I don't really know what they were thinking. But after teaching it in 2011, to the school's credit, they listened to the students, and the students said that this class needed to continue. And it has at UCLA. It's continued since then to today. It will be. I've just signed up a 2-year contract, which is the first time they've ever given me 2 years out ahead. Something must be going right. But since 2011 minus 1 year, where we had a little disagreement about using videos to teach the class, every year except for one, I've been teaching this at UCLA. In 2000, well, let me back up. Cal Poly, my school, the school I went to and graduated the architectural engineering department from in 1988, had decided to cancel the class altogether somewhere around 2010, I think. So it wasn't taught for a number of years at Cal Poly San Luis Obispo until a very influential post-tensioner, Florian Barth, who was incremental in ADAPT software and BFL in Northern California. His son was going to Cal Poly and going to graduate with a master's degree. And Florian was not happy that his son was going to graduate a very distinguished school without having any exposure at all to pre-stressed concrete, where Florian had made his initial money. Florian made the rest of his money in real estate development and purchases and rentals in the San Francisco area. But his seed money for all that came from being a post-tensioning structural engineer. So I happened to be in an event where Al Estes, the department head, Florian Barth was there. I don't know what came over me, but Florian told Al he wanted the class taught, and I offered to teach it for free. Fly up in my airplane every Friday and possibly only teach to Florian's son. Well, it turns out that other students were pretty sharp. They figured out that if I was willing to teach this to Florian's son, and Florian felt this was important for his son to take, that maybe they should take the class too. So they did, and I think I had 8 or 9 students. So I, again, taught it for free, flew up on Fridays, met with the students. We didn't have a classroom. We kind of walked around. We were out in the courtyard sometimes. We, most of the time, crashed the grad lab up there and just had our class there. Again, I think Al had hoped that this would be one and out. He'd appease a major benefactor of the program, and I would go away. But again, the students talked to the school. Again, to the school's credit, they listened to the students. And since 2014, I have been teaching this same class to the Cal Poly architectural engineering students without any interruption. So all that is happening. I've got these videos online. I get all kinds of response from students all over the world, people all over the world, practicing engineers all over the world, upset that there really isn't a strong academic support for this. And that I have no explanation for. I really don't understand it. I went to teaching the class at both universities using these pre-done videos. They've actually been very successful, and this is well before COVID came around. UCLA initially said absolutely not, and that was the reason for our parting of ways for 1 year. But they changed their mind after that, and I've been teaching using pre-recorded videos since then. That has allowed me to teach in person once a week, either through Zoom or live in person on campus. So it's a live discussion once a week, maybe in person, maybe on Zoom, through the 2 different campuses. Or I've had my father or my business partner step in for one of those. But you get a live, real post-tensioning person with all decades of experience. It's usually me, but I am getting help, and I appreciate the help. And it has freed me up, not having to do that 2-hour drive to and from to UCLA twice a week, has freed me up to really be responsive through emails and get on a Zoom meeting and meet with students and help you along. So I think it's been a net benefit. The students who initially were not happy about learning from pre-recorded videos, most of them have changed their mind. By the time they got to the end, they said they appreciated the video, the fact that they could watch it at their time when they were feeling sharp, watch some of it, and then finish up later, rewatch it, use it to study from the exams with. Turns out, this has been successful. I've been teaching to very sharp students for many years now using these videos, and they're learning pre-stressed concrete, I can tell you. I also, by using these videos, have been able to take 1 hour and 50-minute lectures and usually get them in about 1 hour and 15 minutes. And because you're the paying customers, you have access to my notes and our book. So you will be able to just move along with me looking at the notes. Now, in live lectures, I have to redraw all that that same stuff on the board, and that adds a lot of time to a lecture. That doesn't happen in these pre-recorded videos. So there are a multitude of benefits, in my opinion. Okay, so let's talk about you. How do you do well in this class? The first thing to do is do just what you're doing now and watch these videos. Start your homework early. I typically make the homework due on Wednesdays, but I strongly encourage you to start them over the weekend and send me your progress over the weekend. I've committed, again, because I've worked some more time out of it by not doing all the driving and the in-person lecturing. So I make up time for that on the weekends to review your work. And if you will do that, the people who do that do extremely well in my class. You basically get almost a perfect score on your homework assignments if you will approach it that way. One thing I want you to know, so that's how to handle homework and how to do well. I think you're seniors and graduate students, so you probably have a pretty good handle on how to do well in courses now. ACI code. So we're basing this off the ACI 318 code, but an interesting thing is happening in ACI now. Forever, 318 just was the code. If you were talking about concrete, you were talking about the ACI 318 code. Those were synonymous. Because of the popularity of pre-stressed concrete, there will now be two new codes. 318 will no longer be the dominant code for pre-stressed concrete. There's 319 now, and that will be dedicated to pre-tension, precast concrete. And ACI 320 will be a new code dedicated entirely to post-tension concrete. My world, what I do for a living. I think this is a fantastic development, but it sure does say that, hey, pre-stressed concrete is remarkably popular in the industry. If it's going to cause ACI, which is stuck to one 318 code for its entire existence, as far as I know, to now have two new codes, and those two new codes are entirely based on pre-stressed concrete, that speaks to the popularity of pre-stressed concrete. Again, baffling why the school systems aren't following that lead, but that's up to them to decide what they're going to do. I'm doing my part here at UCLA and Cal Poly at least, and like I said, if things go well, we're in discussions to take this course kind of worldwide to anybody who wants to take it. So we'll see where that goes to. I am part of ACI 318T. Andrea Schocker is the chairperson of that. In 318, we, as part of Sub-T, Subcommittee T, we advised the full ACI 318 committee on the things relative, the issues relative to post-tension concrete. The 319 code that is coming along will be chaired by Karen Roberts-Woolman, and the 320 code will be chaired by Carol Hayek. So these women are fantastic. We are all in good hands, and I have a feeling, a very strong feeling, that the things that have been problems in pre-stressed concrete are all going to get worked out. I think these two new codes and the people chairing these codes are terrific people. I have a full confidence that some of my personal frustrations about pre-stressed concrete relative to the code are all going to get worked out. So I'm looking forward to watching that happen. So in this class, I will talk about pre-tensioned and post-tensioned concrete. In the beginning, they're kind of similar. They're the same, really the same general analysis approach. It's not until the implementation that there come to be differences in the code. But I am emphasizing post-tension concrete, and I think that makes this class unique, even relative to the few that are being taught as pre-stressed concrete classes. Okay, let's watch a video of PowerPoint. So, what are we talking about? A lot of you students, these words, pre-stressed concrete, are brand new to you, and they were to me at your age too. Let's look at a two-span beam, uniform load on it. Concrete wants to deflect. Every material wants to deflect. Concrete has a little bit of a worse deflection issue than other materials in that it tends to continue to deflect under creep and shrinkage. So that's a little bit of an issue for reinforced concrete. Pre-stressed concrete basically solves that deflection problem. It solves a number of problems, but one of them is the deflection problem. And that you can kind of visualize here. We will drape post-tensioning tendons through the system. We will pull very hard on those tendons. That drape creates an upward load on the concrete, and effectively we can get as close to a flat floor system as we really feel like we want to. That concept is called load balancing. And we can decide how much of the load we want to balance. Now, some of our load is live load, so it doesn't typically make any sense to balance live load because it's transitory. Maybe there, most of the time it's probably not there. Certainly not at its full value. Dead loads, particularly the dead load of the concrete itself, will always be there. So we are typically talking in terms of balancing a percent of the dead load. You know, we can spend the money, put the post-tensioning in to resist 100% of the dead load and try to make a completely flat system under its own dead weight, or we can use somewhat less. Most of the time, it's the most efficient to use somewhere in the 70 to 80% dead load, concrete load balanced percentage. Changes job to job and person to person, but that's the general area. That's the window that we usually work in. So let's look at some pictures from some of our projects. That is a column waiting for a beam. Most of the time, the beams, and I will be honest with you, most beam and slab systems now are in parking structures. The remainder of other types of occupancies have gone to flat plates. That's probably the most popular post-tension system out there right now. But long span beams in parking structures have been around a long time, and they're not going anywhere. And this happens to be one of ours in the city of Brea. I believe this was the source. Anyway, my good friend Bill Klorman was the contractor on this, and you can tell because his name is on almost everything. These are steel beam forms. So in long span post-tension concrete, the beam forms are usually steel, and the slab forms are usually plywood. So you'll see that indentation from below with the plywood, and a nice clean look on the steel beams. Be careful. If you stand still too long on one of Bill's jobs, you may get spray painted with his name. So try to move around a little bit when we're on his projects. This is the top of the system. These are the beams. These are the forms. These are formed by those steel beam forms. And these are the slabs spanning one way, beam to beam to beam. There's a girder in here picking up. This is going to be the turnaround aisle where the cars turn. But the slabs and the beams in long span post-tension structures, most post-tension structures, they're post-tension in both directions. So slabs in one direction, beams in the other direction. We're going to come back to this slide a little bit later, but this is a construction joint. Most of the time, the contractor cannot pour the entire floor at one time, so it's broken up into various pours with construction joints. And that sometimes is a problem in reinforced concrete, not really in post-tension concrete. And the problem is the lapping that's required in reinforced concrete or mild steel. You can only go 60 feet with a piece of rebar. That's the longest a piece of rebar can be trucked on the highways in California. So you're left with 60-foot pieces. And if you need more than that, you've got to start lapping. Post-tension concrete, we will see that we can fabricate and unroll any length we want, 350 feet if we feel like it. Post-tensioning, one of the many, many benefits is that it effectively eliminates the lapping issue that also exists in reinforced concrete. So this is a close-up of a beam column joint. This is a different job. In this case, the supplier has black sheathing around the strand. In post-tension concrete, the strand itself, the strand is the metal that we're going to see in a future slide. But it's inside, it is greased, and it's inside this plastic. And the idea in unbonded post-tension concrete, cast in place unbonded post-tension concrete, is that the pre-stressing steel is never in contact with the concrete. There's no strain compatibility. All the things you learned in reinforced concrete kind of go out the window. The pre-stressing is doing its own thing, and the concrete's doing its own thing. And that's, I wouldn't say a complication, that's something that makes it very interesting in analyzing and understanding post-tension concrete. Notice we will also always have bonded reinforcement wherever we have unbonded reinforcement. The two will always go together. This happens to be a project that was close to UCLA, and in 2012 I brought a handful of students over to see what we were talking about. So I took some pictures. This is a picture of the tendons coming out. They have been stressed. The stressing of those tendons allowed all the formwork to be removed. So the steel beam forms were removed, the slab forms were removed. This happened 4 days after pouring the concrete. Dramatically different than reinforced concrete, which, if it's not post-tensioned, it has to sit formed for at least 21 days, many times 28 days, to get rigid enough, to get strong enough, and to get stiff enough. Post-tensioning effectively eliminates the need to do that. Once the tendons are stressed, the system will stand up on its own. And it's a tremendous speed benefit for post-tension concrete relative to reinforced concrete. So this is what it'll look like when we're all going to use it from below. I think we've all seen parking structures, so this isn't that earth-shattering. This was a project. This is the Howard Hughes Center. This building over here was the KPFF tower. We worked with KPFF on this project. They were doing the towers. We were doing the parking structures. They ended up moving into this tower. But the interesting thing about this particular slide, this particular picture, is that there's a park on top of this. Now, I will confess that most of that park is styrofoam, but about 15 inches of soil, which is not light, and trees, which have grown up a lot since this picture, and those are heavy, are on this long span beam and slab system. This would not be possible if these beams were not post-tension concrete. I took this picture a year and a half later. Now I'm looking back. This structure was the hole I was standing in, has now been built. This is what that park looks like. Like I said, largely foam, but still, with the soil necessary to support grass, living, and trees, impossible to do without post-tension concrete. And I would say most of the people who go out here and sit and have lunch probably forget or don't know that they're on top of a long-span parking structure. So this is a typical post-tension beam elevation. And since you're the paying customers in this, the end game in this class, at least for the first 10 weeks, is to design exactly everything you're looking at. You are going to do a 2-span beam. You are going to, I'm going to give you the drape and profile because I don't want to grade 30 different designs, but once you have that, you're going to verify everything by hand, all the stresses. You will determine the rebar required. You will determine the stirrups. You will do everything by hand necessary to match PT data, my dad's program that he wrote, and I have continued to modify and work on. You will, by doing that, you will get a great technical basis for post-tension concrete design. So these are the anchors. This is in unbonded post-tension concrete. The only way that the force gets into the concrete, since the tendons are not in any contact with the concrete, it happens at the anchors at the end. Now, it only takes one anchor to end to anchor a tendon at the end, but I'm showing you both sides. So I've shown two anchors in this. This is a tapered hole. The tendon, the strand will come through. I use the term strand and tendon interchangeably. It's not really correct. The strand is just the steel. It's just the 7 wires that are intertwined to create that strand. The term tendon is actually the entire system of strand, crease, plastic sheathing, anchors, encapsulation. It's the full Monty, but I think all of us tend to just use those two terms interchangeably, and I apologize because I will do the same thing. But as the strand comes through, the wedges are placed, and the strand is literally stretched, not just taking the slack out, but stretched, the old PL over AE that you all learned, in order to get the force into the tendons. And every tendon, half-inch diameter tendon, will have about 28,000 pounds in it initially. So when it's trying to recoil back through, these wedges will hang up, lock up, and keep that from happening. So when you were in your reinforced concrete class, you had a variety of bar sizes to choose from. 3, 4, 5, 6, 7, 8, 9, 10, 11, skip to 14, skip to 18. But you had all those choices. In our world, in my world, every strand is a half-inch diameter strand. Now, in the bridge world, and in some cases, there are 0.6-inch diameter strands. But for the vast majority of everything that we do, we're using half-inch diameter strands. So we don't change the size. So this is the Dewey Dag Systems International, or DSI plant in Long Beach. They just need one big, large spool of half-inch diameter strand. And then they will take your drawings and cut to length exactly what your drawings require, the multiple different lengths that are necessary. So this starts off as bare strand. It goes through this gooky machine, and all this stuff is grease. The grease is being applied to the strand as it goes through. The grease has two functions. One allows the tendon to slip and slide inside the plastic that it's going to get. It also is a corrosion protectant. So it's doing two things. It's helping the strand not corrode, and it's helping it move during stressing inside the plastic sheathing. So this is the plastic sheathing being applied. This is hot molten plastic being placed around the strand as it's coming through. And then that strand and plastic will go into this cold water trough, which shrink seals it to the strand. And voila, this is what it looks like, delivered to the site. So again, we can be at any length we need to be. It can just coil up and get placed on a truck, and that's how 300 feet of post-tensioning tendons gets to a job site. Now what you're seeing are anchors that were installed at the fabrication plant. So these are single-ended pulls. We'll talk about that a little bit more later, but if one end is a dead end, that dead end will be applied at the plant. If both ends need to be stressed, then you won't see that dead end anchor on the delivered tendons. So now we're back to that same picture that we saw before, and now hopefully you'll understand a little bit better that those rolls of tendons have been unrolled to become the slab post-tensioning. They go through the holes in the construction joint, bulkhead, and then they'll just sit and wait for the next section, and they'll unroll through that too. So, there's a little bit of a story to this. We do structural observations all the time on every one of our projects. Typically, I'm supposed to be out here the day before the pour, but there was a mix-up. It wasn't my fault. And the day that they told me to show up actually turned out to be the poor day. But I got to get good videos of this happening, so I use this to my benefit. This is concrete being placed, but there's a very important person out here. This person is running the vibrator, and that vibrator is being placed various locations, hopefully throughout the entire bore, and it is consolidating and vibrating the concrete. That person's job is extremely important in post-tensioned concrete, particularly around the anchors. And we hope that a seasoned professional person running that vibrator understands that and doesn't spend too much of his or her time out here in the field and actually gets closer and spends a lot of time by those anchors. Here he is again. And I've noticed from going to job sites for 30 years that the right ratio is about having 2 people actually doing work and about 6 to 8 people standing around watching that work happen. It seems to be the right balance. I don't know why that's so successful, but every time I ever go, that's what I see. There's another story to this video I'm about to show you. I was pretty upset when I saw this. We go to great lengths to encapsulate our tendons, and this is a big mat foundation, so lots of tendons in there. Encapsulation keeps, we'll talk about that in a minute, but it keeps all the elements away from the post-tensioning strand. So really, the metal is never in contact with the concrete, with the air, with the water, with salt if we're near oceans. It's supposed to be entirely encapsulated, as the word implies. But I saw this happening, and I thought, how could it survive? How could that plastic and the grease survive this? But I've learned later it can, and it's all been tested. But that was the main reason I was taking this video. This is how the tails, after being stressed and anchored in, are cut off. That's basically the residual grease just burning at the end. I was afraid it was the plastic anchor or the anchor itself participating in being burned, but turns out it's not, and I'm comfortable now. But even at my age, I'm still learning a lot about our industry. So, I've thrown out the word encapsulation. It used to be in the olden days when I was your age that there was no requirement that the strand be kept away from all the elements. In fact, towards the dead end, the strand was often exposed. The concrete did attach to it. No harm, no foul was the thought, because it wasn't the end that's going to have most of the movement. This was the dead end that was sitting still. So it would be exposed to the concrete. But the problem is it was exposed to all the elements. And if we were anywhere near the ocean, San Diego, Los Angeles, Hawaii, San Francisco, Newport Beach, Marina del Rey, these have all had black eyes, to be honest with you, in post-tensioning. There were corrosion problems, and the post-tensioners had to fix it. And we understood, and encapsulation came around and was available to us, and a lot of us were using it, and a lot of people weren't using it. They were taking the risk. But in 2014, ACI decided that every tendon would be fully encapsulated, regardless of where it existed in a building structure. So this is the encapsulation system. It keeps that bare strand from ever seeing the light of day, ever seeing moisture, salt, or the concrete. Everything's in plastic. Everything's isolated. And hopefully we've solved all corrosion problems. I think we have. So this is a plastic pocket former that will sit in there. It creates this void. It'll be pulled out. this hydraulic jack will be placed, and the nose piece goes in where that plastic former used to reside. This will be hydraulically pulled back, stretching the tendon, which is being grabbed right here. So that's how the force will get in every single one of the strands inside the building. Then, as we saw in the video, this will be burned off. So here's an assisted living facility that we did in Pasadena. Now, this was originally designed as a steel building. It was much taller because it had to be. The steel building needed about 3 feet of depth for the concrete fill over metal deck flutes on top of the steel beams, which were 24 inches deep or so. So 18 inches, typical beams, steel beams. We were able to, through a number of reasons, we worked with the foundations, but converting this to a post-tensioned flat slab saved, I think, almost $1 million, if I recall. And that was back in the early 2000s when that was a lot of money. This is probably the most popular type of post-tensioning system there is, the flat plate with no beams. We effectively create beams within this very thin slab. So we'll create beams in one direction, and we will run uniform tendons in the opposite direction, effectively supported by those beams. When it's all said and done, you're driving by in Fair Oaks Assisted Living Facility in Pasadena, you have no idea if that's a wood structure, a steel structure, or a post-tension concrete structure. So if we weren't cheaper, it wouldn't be a post-tension concrete structure. It would be whichever one was the cheapest. So not only do we have better performance, thinner systems, less weight, we're also less expensive. This is a very popular type of construction of post-tension concrete. This is a podium slab. We wanted to get, I'll be honest with you, a Disney hotel, and we took this one on the cheap. We did from this level, podium level down. Another structural engineer did the wood frame hotel on top. We supported that hotel. This deck is thicker than it appears to be because this plywood is overlapping. But we have a thick deck that we use column caps for because there's a lot of load on these decks. We have a parking deck down below that has no column cap. We just use, which you'll see, as stud rails. Very popular type of construction, residential type. This was another one. This is in Westminster. I think this thing went on for about 700 feet. It was a good project for us. And when it's all said and done, the architect covers everything up, and nobody really knows which parts were wood, steel, concrete, where the concrete level ended. But we know that the owners picked the least expensive way to go, which is what you do. So those are all the good things. Sometimes things go wrong. It is, if we're going to put very large forces into buildings, sometimes it doesn't go wrong. In that flat plate, where I said we kind of create beams within the slab, we bunch up the tendons really close to each other. That creates a situation at the end where there's a tremendous amount of force coming in. Remember, these are stressed to about 28,000 pounds each, and it would not be unusual to have 25 or 30 tendons at one location. So we can easily be north of 700,000 pounds of force being placed over a relatively small distance on the edge of a thin slab. So we, one way or the other, need to reinforce that location and confine it. This is a detail that we use for some thicker podium type slabs. In our thinner slabs, we actually use stud rails themselves now to confine that concrete. But this was a condition on one of our jobs in Fullerton where a little misunderstanding between us and the contractor. We had all of our confinement details on the job. The issue was that they didn't place it at the construction joint because they read the detail to say it was at the end of the building only, but the concrete doesn't know that the construction joint is not the end of the building. And when we put a tremendous amount of force there at the construction joint, it exploded in this case. And I think in the next slide you'll see that the confinement reinforcement of stud rails was actually just sitting over here. It was supposed to go in. You kind of see them just laying over here. Nobody decided to put them actually in the slab that needed it. This was probably 3,500 psi concrete that became dust. Pieces of concrete flew about 40 feet. You know, everybody was in the proper position, and as long as everybody is stressing the tendons safely, you shouldn't really have any threats to life safety, but sometimes some very ugly things do happen. Another thing to be concerned about is overbalancing. Overbalancing can happen for a variety of reasons, but this wasn't our job. But the engineer who did this job only analyzed the slab, assuming that the full building on top of it was there, the full weight of that building. And that's a real common mistake to not understand in post-tension concrete, that one of the controlling analyses is when there is no load there. You have to make sure that the building is okay and safe and stresses are satisfied even when there's no applied load. The concrete and the pre-stressing are the only load. And this is actually a formed deck, so the drape turned out to be excessive here, an excessive amount of post-tensioning, and it led to a series of these bubbles that popped up across this podium deck. So those are the things to worry about. When we're talking about post-tension concrete, I always say, and sometimes this is a test question, the best design is the one with the least amount of post-tension. We want to satisfy the code, we want to satisfy standard of care and practice, but we never want to put in more than is absolutely necessary. This is one of those things that happens, or can happen. So we're just trying to limit how much force we're really putting in the building, and too much force is never a good thing. This is the other direction. You can see from this notch 2x4 what kind of gap we were talking about. This really was a serious overbalance. There was way too much drape in a short span, and that was the main problem here. I'm showing you what I'm about to show you, as it's dramatic, it's good dramatic effect, and nobody ever forgets about these. But this is how punching shear is handled. We don't use these caps these days that often unless it's a podium, and in this case it was a podium, so we would do the same thing. But there is a good trend to remove these caps in the thinner, lighter structures. But this was Northridge. This was a 3-story apartment building over one podium level, post-tension concrete. And had this not been a post-tension concrete, this entire building would be sitting on the ground. This whole thing would have collapsed. The post-tensioning actually saved about 2/3 of this building. It stopped the domino progressive failure effect. So one end of the building, the slab was improperly, or actually just not connected at all, to the shear wall. It was a detail that was a terrible detail. It never got finished, and during the earthquake, the slab just slid off the shear wall. So tremendous lateral movement. There was nothing this corner column could do or some of the other columns could do. They're not designed to go through that type of movement, have that type of bending moment in the slab, and so it punched through. What you're looking at is a little bit farther into the building. This is actually a column. This is a column that looks like it's been shaved like in a pencil sharpener. It's necked down. Looks terrible, except for the fact that it's still standing. It's still acting like a column. And it's not acting like a column because of anything the rebar is doing. I have noticed in my career that whenever there is a kind of a violent event, an earthquake, a car running into a barrier, running into a column, any type of serious impact type loading, concrete tends to shatter off of the rebar. You know, it was once bonded and strain compatibility and all that fun stuff we talk about. But in this case, it looks like somebody came along during the earthquake and cleaned all the concrete off the rebar. The concrete just shatters off of this rebar. So any of these details that rely on bond of rebar to concrete, in my opinion, are going to be useless for this integrity type of reinforcement. Post-tension concrete is the only thing that has any chance of saving the building in a punching shear failure, in my humble opinion. What you're looking at in these green tendons, there are 2 of them that happen to hang up in this direction right over the top of the column. And in the other direction, there are 2 more tendons that also hung up over the top of this column. So 4 post-tensioning tendons are holding up about a 30-foot by 30-foot bay of concrete with a building on it. That's the building to the left. That's the stucco wall to the left. So this is, and yes, my father and I walked below this building on the verge of collapse. One of us took this picture. We both had cameras, so we both took pictures of this. We both debate who took this one. But you can see those 2 tendons coming below that are hanging up over the column and then coming back down. And in the other direction, there are those 2 other ones. But that's it. That is entirely what is holding up the building at this point. And had that not happened, had those tendons not hung up on that column, this would have failed, and the domino effect of the next bay of columns failing, and it would have taken the whole building down. But this arrested the progressive failure. So post-tensioning literally saved the lives of the inhabitants of this building. Didn't save the cars. Cars didn't do so well, but luckily nobody was in those cars. But this was the point at which, just to the left of this, the columns hung up on the post-tensioning, or the post-tensioning hung up on the columns and saved this building from everything to the left of this picture. Today, most of the time, if the loads are light, we will use these stud rails. And Dirk out of Canada created the stud rails, really did a terrific job, did all the testing necessary. It's kind of like Kleenex or Xerox. You know, they patented the name stud rail. But just like we all use Kleenex and we all make Xeroxes, or we used to make Xeroxes, now we make PDFs. But you know, that name has just transcended the whole industry, and everybody calls these stud rails now. They're technically headed shear studs, welded headed shear studs on rails, but we call them stud rails, and Dirk seems to allow everybody to do that. But that's the shear reinforcing. Notice that because I stood under that building and took that picture with my father, I will never forget that. So the code says you need to have 2 tendons in each direction going through the column. We try in the banded group of tendons to get 8. Code says 2, we put 8. And notice that the banded group of tendons act like the beams, and so most of the uniform tendons will go over the banded tendons. And if you think about that, that creates a net that really can't fall. If these tendons stay with the column doesn't go anywhere, they will support these uniform slab tendons that are outside of this column, and hopefully the whole building stays up. That's the running theory right now. Again, putting large forces into buildings can have negative consequences, and our slabs will move. This is out in Palm Desert. There are some very expensive homes, 2-story homes that are about to be built on top of this. We did the concrete box below. We did the podium slab, the walls, the columns, foundations below. Another engineer designed the wood residences up above. As you can, if you look closely, you can see that there is a steel plate here. It's waiting for a corner column that's going to come, a steel column that's going to come. We met with the engineer and said, our slab is going to move. In fact, we have masonite board in between the slab and the wall. Masonite is a material, if you've ever bought cheap IKEA furniture, and you had to put that, flimsy piece of wood, cardboardish thing on the back of your bookshelves. That's what masonite is, and it works better for building material, I think, than it does for the back of a bookshelves. Anyway, we use 2 pieces of those, and the slab tends to slide really well along those 2 pieces of masonite board. But it doesn't if the engineer above puts anchor bolts right through all of the system. And I asked him not to do that. He told me he wasn't going to do it, and then he came and did it anyway. And then we all had to meet out at the job site, and I said, this is what happens. Our slab is trying to move to the right. It's trying to move to its center of mass after being stressed. And it's going to take everything it's hard attached to with it. And we tried to slip this, but with anchor bolts going through the system, it grabbed the wall. And this was only a couple days after the slab had been stressed. My understanding is this got much worse before it got fixed. So these are the things to watch out for. One of my favorite parts of post-tensioning is external post-tensioning used to retrofit, sick old buildings that have had corrosion or something wrong with them, or to just increase their load capacity. In this particular case, this was a Newport Beach project where, because it was close to the beach and it was back in the days, believe it or not, they only wrapped the tendons, they only wrapped the strands in paper, greased paper, and the grease just disintegrated over time, and so did the paper. But then so did the post-tensioning. So the salt air came in every morning, deposits a marine layer down, and it's just eating away at the post-tensioning that's up there. We replaced it using galvanized tendons in sheathing from below. So it still stands today. It's one of our favorite jobs. Every once in a while we'll take students to this job. But external post-tensioning is just a terrific, lightweight, very strong way to fix a building. Now, most other methods of fixing a building involve applying a lot of load in concrete. You're adding or shooting on another slab. You're adding a lot of beams. You're adding something that has weight to it. And then you have to consider that weight on the system, on the columns, on the foundations, on the seismic design. Post-tensioning is, negligible weight and can be applied in a building and give it tremendous strength. So this is that same project. This is actually the sister garage. A few years after we did the previous garage, this one started having worse problems, and we ended up putting a deck over the top of this because they had really let it go. So we had to strengthen the beams to support that new weight. We strengthened the slabs so that they wouldn't fall down, and we designed the new post-tension slab to span beam to beam up above. So this was a fun job. You have to get creative when you anchor these external post-tensioning members. You still have a lot of force coming in, and you don't want it to slide down the column, and nice bearing plates. So these are galvanized tendons, by the way. That's why they're allowed to be somewhat exposed. So here's a hotel out in Palmdale. This was originally designed with rebar decks, 10-inch rebar decks. The entire front of this was designed in steel. And a concrete subcontractor brought it to us and said, hey, can you save money? And we redesigned the decks and post-tensioning, made them 7 inches thick. We took out all the steel in front and made it post-tension concrete too, which saved money. And again, it's all about money. Everything comes down to money. And we saved a lot of it on this particular job. So it was a fun job. We had flat plates, we had beams, we had one-way slabs, two-way slabs. Embassy Suites out in Palmdale gets really hot, so they wanted to bring the pool inside. So this is the gunite pool over here. We spanned some beams across the pool area, post-tension, of course, one-way slabs in between them, two-way slabs out in the tower. And we used metal studs to give the steel the same look that it was going to get before. And when it's all said and done, nobody knows if that's a concrete building or a steel building. They know what it looks like. It looks like this. It's always fun as a structural engineer to be able to go online, Expedia, Travelocity, something, and and look up a hotel and that you designed and get to see the advertisements for it, how much they're getting per room, things like that. This is the inside. I'll admit it probably looks nicer now than it did in the previous picture when it was all concrete, but there is some beauty to the all concrete look to it. But again, nobody knows what this building's designed out of from the inside. Okay, that's the end of my PowerPoint presentation, but not the end of this lecture. Okay, I've got about 20 minutes left for this lecture, and I'll try to get this in here. Most of you young people, when I was a young person, most materials were designed using something called working stress. Allowable stress, working stress, went by a number of names. The concept of LRFD, load resistant factor design, strength design, nominal strength design, ultimate strength, again, those go by a lot of different terms. That was a concept that only was used by concrete. Since I was in your shoes and in your seats, literally, the world has transitioned. Steel decided to develop their own LRFD methods, and that's the most common today. Even wood decided to follow along and came up with an LRFD design to wood. Now, my understanding is wood still, you can do allowable stress design, or you can do LRFD type design, but these are strength based. So you're determining whether or not you have enough strength based upon these allowable stresses. That was the theory. So in steel design, for instance, we would use the actual loads. We'd place them on the member, come up with the moment, and then we would limit the stress, the bending stress, for instance in steel, to 0.66 Fy. And that was, if you did that, you were told that you would have enough strength and factor of safety in there not to fail the system. That wasn't a terrific way to do strength design. So I think concrete recognized that early. Steel and wood came along. Masonry understood that later. And ultimate strength, load resistant factor design is all based upon plastic behavior of the materials now. So the steel's yielding. The concrete, according to Whitney, is at 0.85 F'C in compression. We're looking at, if you're doing a steel beam, it's all at yield. Nothing's allowable stress anymore. Nothing's in the elastic range anymore. It's all at a plastic state. So that's true failure, or that's true full capacity, and that is the right way to do these things. The reason I bring this up is that post-tension concrete, pre-stressed concrete, has actually always been required to do two designs, one based on allowable stresses and one based on ultimate strength. So the strength design of pre-stressed concrete is just like regular concrete. 1.2 dead, 1.6 live, capacity reduction factors for shear, bending, used appropriately. But we still have to do a complete allowable stress design. Now, it's not based in strength, so this part of the design doesn't tell you if it's strong enough, but we're trying to limit cracking is what it really is about. But the point I'm making is pre-stressed concrete, you have to do two full designs. In the first half of this class, we are going to focus on the allowable stress part of the design. The code requires us to limit the stresses in the material to basically below cracking. You're allowed to exceed that in some cases, but for our course, we're going to stay at the 7.5 square root of prime C. When you go out to practice, you'll learn that you can exceed that as long as you do certain things. But we're going to stay academic in this. And we'll just keep the concrete theoretically from cracking in our class. So we have to do that entire design, entire analysis. It's all an elastic-based analysis. We're using elastic section properties, which is why in your first homework assignment, I'm going to ask you to show me that you remember how to calculate elastic properties, moment of inertia, section modulus to the top and bottom, that type of stuff, because we're going to have to use it. Then after we establish all that our stresses are satisfied, we're going to scrap it all and we're going to move over to the more traditional ultimate strength design. So we have to do two really complete designs in post-tension concrete, pre-stress concrete. Now we have pre-tension concrete and post-tension concrete. So that's, what are the differences? Well, let's start with something that you guys might recognize. This is what I like to call pre-Malone. You know, anytime there's a pre involved, it's not going to be as good. Now this is post-Malone. Much cooler version of the same guy. Better music. Everything's come together for him. My kids think he's great. I think his music's very good too, because I'm young, cool, and hip in my own way. But the point here being post. Post is good. Pre-tension, not so good. I'm biased. I'm a post-tensioner. So what does that really mean? Well, I've shown you what post-tension concrete is. That post-tension concrete is basically always unbonded to the concrete. So it's greased, it's in that plastic, it slips and slides, doesn't have any relationship to the concrete really, other than it's pressing against it and squeezing it. But there's no strain compatibility. This is pre-tensioned concrete, and the pre-tensioned means that they literally tension these strands before any of this concrete's ever placed. So what you're actually looking at, these are steel forms. The outside of this is all the steel form. The concrete gets placed in that steel form, and those tendons have already existed and are stressed within it. So the pre part of pre-tensioned concrete means that the tendons were stressed before the concrete got there. That's the pre. Post-tension concrete means the tendons are stressed after the concrete is placed and hardened. So pre and post have everything to do with when the tendons are stressed. So in pre-tensioned concrete, these are the types of members you're going to get. I pulled these off the internet. These are not mine, but they will stress their strands, before any of this concrete is placed in that steel type form. Then pour all the concrete. Then they release. I'll go back to this slide. This slide. So once this is all hardened concrete, then this will get cut. And it's actually the bond, and bond is incredibly important. We are unbonded in post-tension concrete. Pre-tension concrete is bonded. This steel is in direct contact with the concrete. It relies on that direct contact to transfer the tension in the steel to become compression in the concrete. So as these tendons are trying, like rubber bands, they're stressed, they're trying to compress, they're compressing the concrete while they're doing it, and it's through that bond. So there's one thing to understand between pre-tension and post-tension concrete. It's really, in my opinion, the most important thing is the bond. One of them is bonded, this one's bonded, and the other one's unbonded. Ours, post-tension concrete, post-Malone, however you want to think of it, we're unbonded. That's going to become very important in the second half of the course. ACI completely addresses bonded pre-stressing differently than unbonded pre-stressing. So that's what precast, pre-tensioned members look like. They're basically built at the shop. They'll get shipped out. They'll just get placed on site. So it was really concrete's version of steel design. Steel was able to fabricate their members in a plant, ship them out, put it together quickly, and concrete wanted a version of doing that for speed. So we got precast from that. And then they post-tensioned their structures. Or pre-tensioned their structures. Pre-stressed. Okay, I'm not going to spend much time on this, but in your first homework assignment, I am asking you in a variety of sections that I've given you to come up with
the section properties. Again, that's because we are going to have to do, half of our design is based upon elastic behavior. We're trying to limit the stress to cracking or below in tension. We have compression limits, but any good design should be well below those. That's just an academic thing. But this is what you're going to want to follow. I'm not going to go through it, but just to refresh yourself on how to calculate elastic section properties. Now, this is very important, and I hope throughout the course you will refer back to this. There are a variety of definitions here. The first one being the drape of the pre-stressing. The drape of the pre-stressing is its maximum drape between two endpoints. So there's an endpoint, there's an endpoint. Draw a line between those two endpoints, and the tendon is draping between that. The maximum displacement between that line between the two ends we will call A, or the drape. That'll come into some of the calculations we're going to do. Different concept is the eccentricity, but an extremely important factor in what we are about to do. The eccentricity, there are an infinite number of eccentricities that are going to happen. The eccentricity will happen at point to point to point, anywhere, whereas A is one defined point. It's just the maximum drape between two ends. The eccentricity, there's an eccentricity at every foot, every inch along the span of this member. And that is defined as the distance between the CGS and the CGC. So the eccentricity that we're going to talk about and is a very important part of the beginning of our class is the distance between the CGC and the CGS, and there's an infinite number of it. It changes. As soon as you move over, you have a different E and a different E. So understand that. Definition of strand. It's actually 7 high-strength wires all wrapped together. It's not like the number 4 rebar, number 5 rebar, whatever else you're looking at. So you will notice that a 1/2 inch diameter strand, as we get to that point, isn't 0.2 square inches, which would be what the area of a 1/2 inch diameter circle is. It's actually 0.153, because 7 wires don't make up the full density of a 1/2 inch circle. So there's little gaps in there. So tendon, as I've tried to say, is the definition of the strand plus everything else, plus the grease, plus the sheathing, plus the anchors, plus the encapsulation. So the tendon is the full Monty system that gets delivered to the site. The strand is the steel within that. Center of gravity of steel is the center of gravity of the pre-stressing. At least for now, we won't even talk about rebar until we get to the second half of the course. Rebar is used for the strength design. It plays no part in the initial allowable stress design. CGC, center of gravity of the concrete. I will refer to that many times. F, sometimes I will say FE, effective stress, effective force. If there's a sub E or not a sub E, it's still the same thing. I get accused of being a little lazy sometimes. Sometimes I say F sub E, effective stress, effective force, I mean. And final definition, primary pre-stress is the force times the eccentricity. That's not a sub E, that's actually E as in E the eccentricity. E this eccentricity. So this force times that eccentricity at any location is the primary pre-stressing moment. So we are going to draw all of our moment diagrams on the tension side. So if this is not familiar to you, you're probably going to want to study this. The academic, I think we all can agree that a load gets applied, We agree the reaction goes up if the load's going down. The load's going down. So that we follow the shear diagram. That reaction is the shear at the left end. The gradient is the load. If this is 5 kips per foot, then this is going down by 5 kips every foot. So we're all usually on the same page when it comes to the shear design. Remember the deflective shape, but the deflected shape tells us it's easier to look at if it's deflected. The tension is on the bottom. And that's very important in concrete, and it's very important in pre-stressed concrete. Where do we have tension? We need to know in reinforced concrete where we have tension, because that's where the rebar is going to go. In pre-stressed concrete, not only is the rebar going to go there, but we need to check stresses there. And fairly quickly, it can become complicated when you're pushing up on the beam and gravity is pushing down on the beam to know which side is actually in tension. And that's why it's very important that I have you draw your moment diagrams to the tension side. That's going to be where we care. Now, the academic world draws a moment diagram like this. What they say is, well, we take that shear diagram and there's positive shear, so we make a positive moment. When the shear goes to the other side of 0, we start decreasing that shear. So this is the academic moment diagram. The practicing concrete, post-tension concrete engineered diagram looks like this. It's really just the flip side of this, but what we're saying is that we are drawing to the tension side. So instead of just saying positive shear means positive moment, what we're doing is we're looking at that shear, but we're saying where is that shear and that moment creating tension? The tension is on the bottom of the beam. In fact, in this example, it's entirely on the bottom of the beam. It never is on the top of the beam. So the moment diagram, instead of being drawn the academic way, we will draw it to the tension side, which is really just the mirror of the academic moment diagram. If you want to think about it that way, you were taught to do this moment diagram. In this class, you're just going to mirror what you've done. And again, when we're combining loads, some of them going up, some of them going down, we're going to have multiple spans. Your project's going to have 2 spans, so you're going to have negative moment and positive moment. Loads going up, loads going down. It can be easy to get confused, but you won't get confused if you draw your moment diagram to the tension side. Now this is one of the, you may say, I don't need to do that. I know what I'm doing. But this is a very common mistake that young engineers will make. They'll do a great job coming up with the moment diagram. They'll take the soil loading diagram from the geotechnical report, any surcharge, they use the unrestrained or restrained, drained or undrained condition. So you do a great job. You come up with all the loads, triangular load, trapezoidal load, whatever the geotech tells you to do. Come up with the moment, and then young engineers on retaining walls will put the steel on the wrong side. That is, it's actually one of the most common young engineer things to do. Do all the calculations correct and then create a sketch for the draftsman which puts the reinforcement on the wrong side. If you will draw your moment diagrams, as I have, to the tension side, you will always know that that is the side where the reinforcement goes. So if the tension side is to the right, that's where the steel goes in the wall. For the braced wall condition, draw the moment diagram to the tension side. That shows you, that diagram tells you, put the reinforcement on that side. That's where tension is. Gets a little more complicated for multiple stories. This is your tension side moment diagram. This is where your reinforcement needs to go. That moment diagram being on that side tells you it's on the left. Moment diagram moves to the right side. Tells you that that steel needs to be there. And this steel needs to be here. So I'll put a little bit over here for fun. Okay, so tension side moment diagrams, very important. Final thing to get through this, I think I ran a little bit over, but this comes up each year. Remember in your physics class, you had a problem like this, and I had to sit there with my daughter and go through her physics class and solve this too. This problem involved some type of friction. You had a mass here, you had another mass here, and the question was, at what mass level does this mass start to move? We're not going to do that problem, but the way you solved it was to understand that the force in this cable was the same as the force in this cable. Didn't matter that it took a turn. And that's the theory that we are working with in pre-stressed concrete. The tendon or the strand takes a turn. It still has a constant force in it. A lot of people get confused with truss theory, and they say, well, I've got the tendon coming along here, but then it turns, and it must change its force value, because that's what happens in trusses. We're not designing trusses. We're using cable theory. This gets resolved in components, and each node has to be in static equilibrium. That's a truss. That's a node of a truss. That's a different thing than we are doing. So I hope that's clear to you. Our cable, regardless of what shape it takes and what direction it takes, how we bend it and what we bend it around, if we put 200 kips in it, it's going to have 200 kips at every point. Okay. Thank you for listening. That's the end of the first lecture.